Okay, let's start. Good afternoon, everyone. I'm Sogat Kesi, and I'd like to welcome you all in this webinar on Introduction to Spacecraft Dynamics and Career Prospects with Pratiwi Kusumawardani, organized by SOS Astronomy Club as a part of our World Space Week celebrations. Pratiwi is from Indonesia. She's a flight dynamics engineer and an orbit analyst of the Spacecraft Operations Center team for the Bank Rakyat Indonesia satellite, which is a communication satellite for banking purposes. She's also the founder of SpaceID, which is an organization devoted to developing space education and awareness in Indonesia. Prativi ma'am, I'd like to thank you for accepting our invitation on such a short notice. It is an honor to have you with us today. I think we can start now. So without further ado, I'd like to invite Ms. Pratiwi Kusumawardani to give her presentation. The virtual floor is yours, ma'am.
Thank you. Let me share my screen first. All right. Can you see my screen now?
Yes, we can.
Okay. Thank you so much for inviting me, and it's such an honor for me to be here with you guys all. And I would like to share about introduction to spacecraft dynamics and space career. So I believe that you guys are interested in space, right? And I heard that you are celebrating World Space Week, and this is one of the event. So I will just give an introduction. Well, my mission here now is to give you something interesting so that you can explore more after this. Okay, let's start it. So welcome. I always have this motto, invest in space, own the future. This is what our motto in SpaceID, one of my activity here. So space is really big, and I believe there is always space for you if you are interested in it. So I hope you can invest as much as time you have to do something in space so that you can own the future. Okay, there is so many things that you can learn about space. Here I write the main point that you might be interested. The first thing is about the mechanics. It concerns with the behavior of physical bodies when subjected to force or displacement and the subsequent effects of the bodies on their environment. The second one is a C, celestial mechanics. Motion of celestial objects, orbital mechanics. Also, we or some of us call it astrodynamic. Motion of artificial satellite or space probes or ballistic missiles and their orbits or trajectories, Caprolian orbits and real orbits. And I believe that you guys also know how to do the observational, but it's also interesting to learn celestial mechanics. And the third one is space or outer space. It's kind of Earth atmosphere, solar system, and where we can limit our scope. Because as I mentioned before, the space is something that really big, so we need to limit where is our scope. And then the last one is mission and analysis. As you may mention before, that I work in a spacecraft, one of the satellite that owned by bank, the only one bank that has its own satellite and also operate it by our own self. We believe that there is so many mission in the satellite itself. So we need to know what is our mission, what is the function, and what is our goal. That's so that we can analyze and do what's next for our mission. Okay, so let's get started. As you may know, Earth is the only planet in the solar system with an atmosphere that can sustain life. The blanket of gases not only contains the air that we breathe, but also protects us from the blast of heat and radiation emanating from the sun. It warms the planet by day and cools it at night. Earth's atmosphere is about 30 miles or 48 0 kilometers thick, but most of it is within 16 kilometers the surface. Air pressure decreases with altitude. At sea level, air pressure is about 40.7 pounds per square inch, uh, or at 3 kilometers, the air pressure is 10 pounds per square inch. There is also less oxygen to breathe. As you know that we have different type and temperature on the atmosphere. So for the example, if the stratosphere starts just above the troposphere and extends to 50 kilometers high, the ozone layers which absorb and scatters the solar ultraviolet radiation is in the layer. Each of these steps, I believe that it will have different condition, and we will also have different temperature variation, so that we will have different things to prepare if we want to do, let's say, the mission. Okay. Well, we'll start with introduction to celestial space. If we already talked about the atmosphere, we'll start now with the introduction to celestial space. As you can see here, if we are here, um, as I write it as a human here, and then this is a zenith. You may know that meridian is a grid circle on the celestial sphere passing through the celestial poles and observer's zenith. An observer's celestial meridian is not a fixed reference on the celestial sphere, but rather changes with the observer location on Earth. Stars transit an observer's celestial meridian that is crossed directly overhead in the sky at the location, once every 24 hours, also called local meridian. In the equatorial coordinate system, a grid circle on the celestial sphere passing through the celestial pole vernal equinox. It represents the 0.4 the horizontal coordinates in the system, having a right extension of 0 hours. This is the basic of introduction to celestial space that you really need to know. And the other important thing is about vernal equinox and autumnal equinox. As you know, that when we are having a spacecraft, the season is also affect the part of the spacecraft. So we need to know what we need to do or what we need to analyze it related to temperature and so on. So what is the vernal equinox and autumn equinox or any other season? So basically, when the sun is exactly above the equator and day and night are the equal of length, and the celestial equator intersect. In the northern hemisphere, the vernal equinox fall about March 20 or 21, as the sun crosses the celestial equator going north. And in the southern hemisphere, the equinox occurs on September 22 or 23. When the sun moves south across the celestial equator, according to the astronomical definition of the season, the vernal equinox also marks the beginning of spring, which lasts until the summer solstice. It's around June 20 or 21 in northern hemisphere and December 21 or 22 in the southern hemisphere. When we talk about the spacecraft, we need also to make sure that the spacecraft is on its right position. Thanks to our scientists such as Tycho Brahe, Kepler, and Isaac Newton that make a big history in science. So we can know and learn about Newton's law, universal gravitation, Kepler planetary motion, and two-body problem analysis, orbital elements, maneuver, etc. The biggest law that we need to know is also about Kepler's law. As you know, first law is the orbit of each planet in eclipse with the sun at one focus, as you can see on the picture here. And the second law is the line joining the planet on the sun sweeps out equal areas in equal times. And the third law is the square of the period of a planet is proportional to the cube of its mean distance from the sun. From that great Kepler's law, we know what we call as classical orbital elements or Keplerian. So this is the sixth Keplerian orbit that can help us to predict or to know where is our satellite. The first thing is semi-major axis, the second one is eccentricity, the third one is inclination, the fourth one is argument of periapsis, the fourth one is association of ascending node, and the last one is the anomaly or time of periapsis passage. These orbital elements will mathematically describe an orbit in space, and these parameters are enough to define the location of a body in space moving in any Keplerian orbit. So what's the meaning of each parameter? Okay, we can summarize is at, we can see on the table. So we can define if the satellite orbit is a circle, ellipse, parabola, or hyperbola. Usually for communication satellite, the orbit is in circle and the radius semi-major axis is equal to the radius. And about the eccentricity is equal 0 or near 0. It can be 0 point something. And what is the semi-major axis itself is one of half of the major axis and its satellite mean distance from its primary. So semi-major axis describe the size of an orbit. Semi-major axis describe the size of an orbit, so we can know what kind of orbit and how we manage this orbit. And then about the ellipse orbit, usually for lower satellite, the semi-major axis is more than 0, and the eccentricity is between 0 and 1. And the eccentricity is the distance between the foci divided by the length of the major axis, and it describes the shape of an orbit. And this is also an important parameter of the Keplerian, as you know, maybe the inclination. And zero inclination indicates an orbit above primary's equator in the same direction as the primary's rotation. As you know, if the inclination is 0, we can call it geosynchronous, and geosynchronous orbit, satellite is usually used for communication, such as BRIsat, where I'm working on. So how is it so far? Maybe that's so basic and you maybe already know about that, but I hope after this you can gain interest in space field. And maybe first of all, let me tell you what I do in daily basis. So I'm doing flight dynamic engineer or orbit analyst at BRIsat. Maybe some of you have ever listened that, and my main responsibility is first, spacecraft orbit determination based on data ranging and tracking. The second one is spacecraft propellant counting and expected end of life. The third one is approach event prediction or maneuver plane. And the last one is maneuver performance analysis. Okay, so what is it and how it go? So basically, we will always have the mission, as I mentioned in the very beginning of the slide. So we need to know our satellite, is it Earth pointing or inertial pointing, controlling during delta V burn, spread payload platform, accuracy or stability needs, and what is the orbit, what is mission life, and so on. After that, we can try to learn more about the other subsystem. Usually, spacecraft has thermal subsystem, command and data handling subsystem that can help us to process the data capability, and also propulsion to make sure thruster size, propellant load, and the communication, how is the antenna pointing accuracy and the power, and also the power is related to solar array pointing requirement. Do we need it to always facing the sun all the time, or what is our minimum requirement for the power? And the most important thing is also the structures. As I mentioned about the atmosphere before, we really need the structure of the spacecraft that can help us facing all that condition. So first of all, we need to learn about center of mass constraint, inertia constraint, flexibility constraint, thruster location, and also sensor mounting. And this is the most important thing also is about attitude determination um, system. So what is it? Basically, we want to know how and where is our satellite, but how we can move the satellite to its position. We will need the ADCS system here. And maybe some of you are wondering, what is the difference about aircraft? And of course, maybe some of you guys know, and maybe many of you have already fly with it before. But basically, they use similar mechanical concept. So what is the difference? Aircraft fly through air and spacecraft fly in space. In space, there is no air. And so a spacecraft cannot be designed same as an aircraft. There won't be drag or lift. When the aircraft have drag and lift, there will be no drag in the space. So we will need to have a different structure for the spacecraft, and also there will be a different subsystem also for the spacecraft. Also, spacecraft have to carry their own air along in the form of oxidizer, since there is no air to make the engines work. That's why many of my friends asking why jet engines can't work in space. So rocket engines must be used instead. Okay, spacecraft flight dynamic is the application of mechanical dynamics to model how the external force acting on a space vehicle or spacecraft determine its flight path. Flight dynamics basically depends on disciplines of propulsion, aerodynamic, and astrodynamic, or as I mentioned before about orbital space or orbital mechanics and celestial mechanics and so on. Basically, spacecraft dynamics are controlled through ACS or attitude control subsystem. So what is attitude control is it? Attitude control is the process of controlling the orientation of an aerospace vehicle with respect to an inertial frame of reference or another entity such as the celestial sphere, certain fields, and nearby objects. Controlling vehicle attitude requires sensor to measure vehicle orientation, actuators to apply the torque needed to orient the vehicle to a desired attitude, and algorithms to command the actuator based on sensor measurement. So there is a three type control in attitude control subsystem: attitude control, momentum control, and also orbital maneuver. So if I go a little bit more about spacecraft attitude, how does it work? So basically, it has the three things that I already mentioned before. The first thing is controller. The second one is actuator and sensor. So first thing first, we need to know what kind of sensor that we use. For example, we use Earth sensor and we measure attitude and rate, and we find the rate or attitude difference. So we define it, and then here we can decide, is it already in the right or desired attitude, or we need to improve on something. If the value or the value is need to be changed, or the attitude is not what we desire, so we need the actuator to do something to give us a torque so we can make a spacecraft dynamics moving or pointing to something. And then The example of actuator here is reaction wheel and biprop thruster. Maybe some of you already heard about the reaction wheel or ring Russell gyro and so on. Let me give a little bit definition of ring laser gyro here. A ring laser gyro consists of a ring laser having two independent counter-propagating resonant modes over the same path. The difference in the frequency is used to detect rotation. It operates on the principle of the Sagnac effect, which shifts the nose of the internal standing wave pattern in response to angular rotation. So it depends of what mission and what satellite we are using here, what sensor the spacecraft is using, and what actuator that we use. We need to define it. And the second one is about the control loop or momentum. In momentum, we will see the difference. Here is if before we see that Earth sensor in momentum control, we see reaction wheel. So reaction wheel is a type of flywheel used primarily by spacecraft for three-axis attitude control, which doesn't require rockets or external applicator of torque. They provide a high pointing accuracy and are particularly useful when the spacecraft must be rotated by very, very small amounts, such as keeping a telescope point at a star. So, and here in actuator, we also see the biprop thruster. Basically, the concept is same, but the sensor is different. And the output here is also angular momentum. And the third or the last control loop here is orbit. As we know that we already learned a little bit about the orbital parameter of Keplerian, here we have also the difference in sensor. We get the sensor it's from the antenna on the ground. So basically we do the ranging and then we get the position of the satellite. Where is our satellite right now? And then again, we target or we compare it with our target of parameters. We measure the error and we try to command the actuator if we need to move the satellite. Let's say, hey, satellite, go this side a little bit, or hey, satellite, go this side a little bit. And we use the biprop and or SPT thruster to move the satellite. So we have the delta V or velocity, and then we can make the satellite stay on its right orbit. And maybe some of you wondering what is biprop thruster or SPT thruster. Basically, the thruster is a propulsive device used by spacecraft for station keeping, attitude control in direction control system, or long duration, low thrust acceleration. So we also need the thruster to go to launch the satellite using the rocket, and also for the on-orbit mission or daily maneuver, we need also the thruster. Okay, to summarize, here is the hardware or components that we need to do the spacecraft dynamic. Of course, there's some more of it, but first is a sensor, the second one is controller, and the third one is actuator. Okay, as we already mentioned before, that we need to define first what is our mission so that we can define where we need to put our satellite. Is it in LEO orbit, MEO orbit, or GEO orbit, or HEO orbit? So basically for communication, we put our satellite here in GEO, and then for navigation, and then for navigation we use MEO orbits such as a GPS and then also GLONASS, etc. And for the really close to Earth is LEO orbit. So the majority of LEO orbit mission is to observe the Earth. So I think I just want to show you how it works to do an orbital maneuver. So basically, we see where are we, and then where we want to be. If we are here, or maybe let's say it's Earth, and if we want our satellite to move somewhere here, we know that we need something to push our satellite so that the satellite can move here. So why we need the delta v or delta velocity? Because we know that our Earth is having the gravity, so we need to calculate how much the velocity that we need to push. And here we get the help from the thruster to give the delta v here, and then we can move somewhere here. Again, it depends on the mission, what kind of maneuver that we can do. And it's a little bit definition of the coordinate system. There's so many coordinate system in space, and you can learn more about it after this, maybe at home. But basically, we can see the spacecraft as fixed orbit, or we can also see Earth as a fixed orbit. So there is so many things, and also we can see role Pichau coordinates. So if this is the Earth and let's say this is the spacecraft, we can see the roll axis here, the yaw axis, and the pitch axis. This is the direction of the spacecraft moving. And also celestial coordinates. And as we know that we mentioned there is a vernal equinox, we also have to observe the season of the satellite will affect, because we need to prepare how many power that we have to make our satellite stay on surface. So we need to calculate how many power and then how many power generated from the solar panel and so on. So basically it's the resume of the coordinate system in space. Okay, here we are, and I'm talking about my space career journey. So I hope you can get a little bit interest on that, but basically I didn't start it like directly to flight dynamic engineer. My background basically is my undergraduate is from astronomy, and then I continue my master in aerospace engineer, and here I end up now as the founder of SpaceID, and also I'm working as flight dynamic engineer or orbit analyst, and I also become an assistant manager here. So it's not easy, but well, if you kind of interest in space, you will find a way. So always focus on what's your vision. I always have a vision to make a giant leap in Indonesia, focusedly and also in the world, space business, management, and education to support other countries' space sector. It's related to science and engineering, but you couldn't forget that space is also talking about the business. And to make sure that all of it delivered successfully, we also need to think about the education. So how to start a space career? So as I already told you that we need more than our knowledge. I mean, we need also to have network up and down, communicate well and often, and hone your skill. And don't forget to establish your goals. Be passionate about what you do, demand reason, and set priorities. Okay, a little bit story that I can share to you that is um, I don't know what is space at first, and I feel like I know nothing about space, but I always see the challenge and try to be the growth mindset instead of fixed mindset. I try to face the challenge as an embrace for myself, And when there is coming an obstacle, I persist despite. While the fixed mindset give up easily, I don't want to give up easily. And maybe you will start see effort as path to mastery. So let's say you face something and there's a change for you, and you feel like you didn't deserve to that position. Just try it first and um, enhance your skill and do something better. And if there is a feedback, learn from the criticism, because sometimes, however the bad, however they give a critic to you, but there is something that you can learn from it. And then don't forget to be inspired, but because sometimes someone that you think that is your idol from you were kids, you can be someone tall beside him when you already get to some position. And then how about the opportunity? As you know that maybe Manisa also said to you, I get a chance to go to NASA, US Department of State, John Hopkins, and also NatGeo, and also the Washington DC, and so many places. Can you imagine if there is a chance for you on, let's say you are only first year of your undergrad, or you are the second year of your undergrad, and there is a chance to you, just try it. Don't let the opportunity go, just go away. So just try it, and then you will see where is the opportunity can lead you. And here is also the thing that I always share to my friend, that none of us, including me, ever do great things, but we can all do small things with great love, and together we can do something wonderful, because we can do it all alone, whatever our nationality or our age, our background, we can do something greater if we are together. And don't forget to share and publish your idea, because maybe someone waiting for you to share, and maybe someone is already waiting for your help out there. So don't forget to share and publish your idea. And always remember, unless you try to do something beyond what you have already mastered, you will never grow. And space is for everybody. It's not just for a few people in science or math, or for a selected group of astronauts. That's our new frontier out there, and it's everybody's business to know about space. Thank you.
Thank you for the wonderful presentation. So the theme of the World Space Week 2020 is Satellites Improve Life, and your presentation perfectly resonated with the theme. Once again, thank you for accepting our invitation and coming here and giving presentation to our participants. You're truly an inspiration for all of us. So
Thank you.
now we'll go on to the Q&A session. So if the participants want to ask a question, they can either write questions on the chat, or you can raise your hand and we will unmute you so that you can ask a question to our speaker. So does anyone have any questions? Please raise your hand. Or so when you are writing your questions on the chat, do not send it directly to any of the hosts or co-hosts, but rather you should send it to everyone so that everyone can see what the question is and they can think about the answer also. I don't think anyone has any questions. Okay, we have a question from Anupam Adhikari. He asks about the stages of satellite in the launch.
Okay, for the stage, thank you for the question. Sorry. So the stage for the satellite launch, there is a few type of stage. Maybe you mentioned about the stage of the rocket, but again, it depends of the height that you want to be. For example, you cannot use the same stage if you want to go to LEO orbit, or you cannot also use the same stage as we want to go to GEO. It depends on the payload that you want to launch, how big it is, how much is the mass, and then also you can also for nowadays, you can also have the piggyback satellite. Or what is it, the piggyback satellite? So basically, the small satellite using the same rocket with the bigger or the GEO satellite. So the launch cost is less expensive, much less expensive than the GEO satellite, but we can use that one. So I cannot answer exactly, but there is different stage for different mission and different payloads.
Okay, so I have a question from Mr. Biraz Kharka. So he asks,
Mhm.
what propellants are used in satellite of
Mm,
BRIsat?
okay, we use MMH, and basically we used to, so for the propellant of the satellite, we used two kind of thruster. The first one is bipropellant, and the second one is stationary plasma thruster. So we use MMH and duo 04. So we sometimes use the biprop, and it depends on what the delta V we want to have at the week. Basically, we do the maneuver plane once a week, but we have around 10 at 10 SPT maneuvers each week, and then around 1 to 2 or 3 biprop each week. Different. It depends on the delta V that we want to have, and then about the maneuver planning, also it depends on the operator. So let's say the BRIsat have that kind of things, but the other operator may have different things. Let's say they have the maneuver planning uh, every once every two weeks, or one every a month. It's different. So that's the answer. I hope I can get
Yes.
the answer.
Shekhar Chaudhary asks, what are the risks of satellite derby in the space for future missions?
The risk of satellite debris. Oh, okay. That's
Debris,
one of
I'm sorry.
satellite debris. Yeah, that's one of the function of the maneuver planning, so that we can decrease the risk of the satellite. But we also analyze in geosatellite operation. We also analyze the possibility that we can have the conjunction with the satellite debris. So basically, we have so many catalogs in our system, and also we compare it with our satellite position, and then we see if our satellite have a conjunction probability with the satellite debris, or this satellite exists. We analyze it, and then that is also one of the things that we need to consider when we want to do the maneuver planning. And maybe a little bit more about the satellite debris. There is also company that are working on it. So we hope that the debris is still in on it's the right position. And also for the GEO satellite, we need to move to the graveyard orbit. It's around 300 kilometers above the GEO satellite orbit. So after our lifetime, we need to move our satellite to the graveyard orbit.
Okay, Anupam Adhikari has asked another question. That is, how is
Mhm.
satellite controlled from the ground upon its orbit of travel in space? Are there any dangers in the mistrack of satellite in space-time?
Okay, so basically, how is the satellite controlled from the ground, right? The question is that.
Yeah.
Okay, so as I mentioned before, we have the ranging. Ranging system is some kind like we give a signal to our satellite, and then the satellite give it back to us, and then we can get the data from the satellite, and then we save that data as a range, azimuth, and elevation. From that data points, we can learn, and also we can know where is our satellite position. We did it every once every 30 minutes. Yeah, once every 30 minutes or 50 minutes. Yeah, around that. And then after that, what we need to do is to make sure that our satellite are on its right orbit. So we do the commanding. What is the commanding? So basically, we send a signal that contain a message to the satellite, so that the satellite can do the whatever we want to do. For example, we are analyzed that our satellite a little bit moving from the right position. We tell the satellite that you should move a little bit to the this side or this side, and then after we analyze that, we give the commanding to the satellite, and we see if it's already moving or not by various parameters. And then also we also need to make sure that our components in the satellite is on its good condition or health condition. So there is some of procedure that we need to run, so we can know if our satellite subsystem or component is healthy or not. We also have a backup of each component, so we do this procedure to make sure that our satellite is still good. So that's how we do the commanding.
I don't think we have any questions now.
Okay.
So we will end this session after 3 minutes or so. If anybody wants to ask a question, so you can ask right now. If not, we'll end the session for all. Okay, so I don't think there are any questions. So thank you for coming and giving this presentation to all. Okay, Viraz Kharka asks, what motivates you to love space?
What motivate? Okay. Basically, maybe I'm just a regular person like all the children. That first, I really love to see the moon, and then I love to see the sky at night. But the thing is, I don't know why and where specifically I love the space, but I try to find a way. So basically, my parents coming from social background, none of them is scientists or engineers, but I'm interested in that field, and I try to learn more about that. And then basically, I don't know, and I really don't know what is astronomy and space, but I try to open the opportunity. And then when I go to undergrad, I see that there is many opportunity that I can apply. And on my second year of my undergrad, I see I can get this first for my winter school, the first time in my life to go abroad. And then after that, there is so many opportunity. I can to the winter school conference and all. So what I want to say to you is just focus on what you are passionate about and try to find something that can help you. If somehow you are not there for your passion, Just believe that somewhere or sometime and someday you will find a way to be balanced between your work life and your passion life. So just trust yourself and keep learning and keep trying.
Okay, the other question is that they want to know about your organization. So they want to know about SpaceID.
Okay, so SpaceID is the organization that basically we want to help spread space awareness and also education and also business, and also in Indonesia, here in Indonesia also there is still not much people interest in space, so we cannot deliver that. And we also have several courses. It's different. We have the free and we have also the paid courses. Depends on the advance of the classes. And we also have collaboration with the industry that we are still working on right now. And we also give the, let's say, the mentoring to the youngest generation to help them to get to the space career and space field and many more. You can follow us on Instagram.
Okay, so Shekhar Chaudhary is asking, what are the layers of satellite communication?
Layers, what do you mean by layers?
I don't know what he's trying to say, but he has written a question which just says layers of satellite communication.
Oh, I need to know more what layers he is mentioning.
Yes, Shekhar, can you please elaborate your question? You're not short on time, right? So
You mean the frequencies or?
oh, he was asking about different physical layers of communication with ground and with ground stations.
Okay, maybe he's refer. I don't know if it's answer his question or not, but basically we have ground communication, different frequency for the ground communication and for the spacecraft itself, and we also have to make its own secure mode. The satellite basically send the commanding and as no sorry the ground is basically send the commanding with specific frequencies or maybe layers that you mentioned. I'm not sure what's the question, but we have the frequency to send the command, and then it's encrypted, so we make sure that our commanding is secure, and then satellite receive it with its own antenna, of course, and then after that, the satellite encode it and try to do something what's our need and do something on the subsystem of the satellite, and then after that, if it's successful or not, what they did, they still need to deliver to us what we call it as telemetry. So it's also have the frequency, and then we get the telemetry in our ground system, and then so we know what the satellite doing right now, and then if the commanding successfully or not, and that's maybe the thing that I can answer, but I'm not sure if it's answer the question or not. I hope I can answer.
Okay, I don't think we have any questions now, so we will end the session. But first, I'd like to thank Monisha Kanel Didi for connecting us to her. And I'd also like to remember Monisha Dua ma'am of Nepal Astronomical Society. And I'd also like to thank everyone for participating in the program, Ayush, Kusal, Pratik, who helped us. So thank you, everyone. We will end this session. And special thanks to Pratiwi Kusumawardani for coming here and presenting her topic and helping us know more about satellites and other things. So
Sure, thank you so much. It's such an honor to be part of the webinar. Thank you.
Thank you. So I'll end the meeting, okay?
Okay, sure.
So thank you, everyone.